These slides are the second part of the lectures on interpolation, approximation and interpolation as part of the computational methods course. So this constitutes lecture 2. And the objectives for this part is to start to look at differences between regular and irregular sampling in the context of interpolation, and to learn a bit about familiar methods for approximation and extrapolation, where we start to find estimates for functions out of their sample range. And then we'll look at popular methods for 2D and higher dimensional data interpolation. And we'll look at interpolating on a regular lattice, for example, in a digital image, or on an irregular structure like a triangular mesh. And then we'll briefly look a bit about convolution as well at some point in the slides. So here's a basic outline. We'll look at approximation and extrapolation. We'll look a bit into interpolation and approximation as convolutions. And we'll start to look at higher dimensions, either as regular data in the form of bilinear interpolation, or on irregular data, where we might look at meshes and use barycentric coordinates to do interpolation there. So if we remind ourselves of the interpolation condition, that meant that for a set of data points where we take some measurements, the y's are the measurements and the x's are the locations, the interpolation condition says that we should find some function that actually equals our measurements at our knot points. Now for approximation, on the other hand, we relax this condition a little. We simply seek a function f such that we approximately match our measurements at each of our locations. We accept that there might be some error in the model that we use, or maybe some error in the measurements that we made for our data. So here's an example of an approximating function for some data. So the red points show our data measurements. The marks along the bottom here, our x's, show the knot points. And the data are scattered around, and we've placed a linear polynomial, a polynomial of degree 1 that approximates our data. It doesn't go through every data point exactly because we've relaxed that condition. We're not interpolating the data anymore, we're approximating it. And of course we can choose another model instead. So for the same data we can have a quadratic polynomial, and you might be able to see that this quadratic polynomial is perhaps a closer fit to our data. And we can choose another model as well. We can go for a cubic polynomial as is shown here. So each of these approximates our data rather than interpolates it. So for each one of those models we can calculate an overall error. So we can loop over all of our data points, and we can look at the function's value for that measurement and compare it to the actual value for that measurement, and we can find the difference between them, and we can do that for every one of our data points from the first up to the last. And if we square all those differences and add them together, we get an error known as the sum of squares error. And we can write the same sum of squares error as in summation notation. So we make a summation here. IR index ranges from 1 up to n, and we're looking at the difference between the function evaluated at the xith location and the actual measurement yi at that location, and we're squaring all those differences and we're adding them together. So here's our value given by the approximation function, here's our observed measurement, and this just reiterates the fact that we're talking about a sum of squares error. So looking back at the data that we saw in the previous slides, we can kind of illustrate the error. So these the red points are still our data points, the same data points in each of these diagrams here. This is the linear model fit, and this is the quadratic polynomial fit, and this is the cubic polynomial fit for each of these. And you might be able to see that the errors actually do, on average, go down as we move from the left of the diagrams to the right. And this kind of illustrates a bit of a trade-off, because we can have either on the left-hand side perhaps a larger error but a simpler model, or we can move to the right-hand side and say, well, we'll take on a more complex model to get a smaller error. So the problem is that as we move towards more complex models, we might end up overfitting our data and having too elaborate a model. On the other hand, if we choose a very simple model, there might be an unacceptably large error. So there's a trade-off to be made between those two competing aims of having a good fit and having a simple model. So looking at it a bit more practically then, if we want to carry out approximation practically with a tool such as MATLAB, we might have some data consisting of locations and measurements from x1, y1 up to xn, yn, so we have n observations. And if we can specify that we have a particular degree of polynomial d that we would like to be able to use to approximate our data, then MATLAB actually has a tool called polyfit, polynomial fit, and this will find us the best fitting polynomial for our data in the least squares sense. So that phrase, in the least squares sense, is something that crops up quite a lot, and all it means is that the polynomial that we end up finding will be one that minimizes this sum of squares error, this error that is based on looking at the difference between the measured value and the function value across all of our data points and squaring those differences and adding them all up. So basically this MATLAB function polyfit takes as its input our data, our observed data, and the degree of the polynomial that we would like, and it provides for us a polynomial, which if you look into the exercise, we'll see what form a polynomial can take in MATLAB. So in summary, for approximation, we should mention that we've only considered approximation with polynomial functions. So and we can represent a simple model in this polynomial function by a low degree polynomial, because a low degree polynomial doesn't have many coefficients, so there aren't many parameters at all. Whereas if we want to have a complex model, we can use a high degree polynomial. There'll be more coefficients to represent that polynomial, and so it'll be we are more capable of controlling its shape. But we have to say that there are other types of model that we can use to approximate data, so not just polynomials. So we can use splines or trigonometric functions or whatever. But the issue of whether to use a simple or a complex model and whether to tolerate a higher or a lower error, that trade-off, that issue will still remain, even if we use different models, i.e. different from polynomials. If we turn now to extrapolation, this is similar in a sense to interpolation, but as we discussed last time, when we extrapolate, we're trying to find a value for our function that is outside the range of the original measurements, outside the locations where they were measured. And in that case, what we're going to need is an explicit form for our function, like a polynomial with some parameters that we can evaluate anyway. The piecewise methods we've looked at won't work anymore, because piecewise methods tend to be fitting functions only for subintervals of our original data. And that means that they're restricted to the range of the original data. So here's an example to show some measurement values, and the locations where those measurements are taken, that defines the support of our data. And what we're going to need is to be able to try and find a function that we can evaluate our estimate at outside the area of the data support, beyond the range of the original data. So if we use a polynomial, we can use one, fit one to our data in the same way that we did for approximation. In other words, we can call a function like the polyfit function in MATLAB, and that will provide us with a polynomial that we can approximate our data with. And then basically we have this polynomial, we have its functional form, we have its coefficients, and then we can evaluate that, that function outside the range of our original data because we have this explicit function. And this ability to estimate a value for a measurement outside the original support is obviously what defines extrapolation. And here's this just illustrates what our extrapolation estimate would be for the data that we've measured here. Whether it's correct or not is a separate matter. It's just that we need this explicit function to be able to extrapolate our data. Let's now look at interpolation as a convolution process, and so this should relate to some of the work you've been doing in some of your other courses. So we can look at interpolation as a convolution operation, but the first thing that we're going to need is a kernel to carry out this convolution. This is an essential step in any convolution. And here is the kernel that we can use for piecewise linear interpolation. And it's defined by a piecewise straight line function. It's 0 almost everywhere, except from the interval between -1 and 1. And what it does basically is it rises up to a value of 1 at the middle at x equals 0, and then it drops back down to 0 again in a straight line. And here's the actual functional definition for it. So I've written it as h of x here. I should probably call it h linear of x with a suffix here so that we can tell it apart from the kernels that we might use for a different interpolation scheme. But for now we're just going to drop this suffix here and just write it as h of x for simplicity. So how does it work? As ever, we always start with our data, our measurements. There are 4 knot points here, x1 to x4 as an example, and the measured values, the y's, represented by the heights of each of the coloured dots above the knot point locations. So the first step is we take each of our measurements in turn and we take a copy of our kernel that's been shifted so that it's centered at the corresponding control point, at the corresponding knot point location. So in this case we've got 4 data points given by these different colors, and what we've placed is a shifted copy of the kernel. 4 copies of the kernel are all placed along the x-axis here. And in terms of notation, this is just the notation for each shifted copy of the kernel. So this will be h, but evaluated at x minus x1. That centers it here. And h at x minus x2 is this kernel here, centered over x2. And h of x minus x3 is centered here. And the final one is h evaluated at x minus x4. So it's just shifted copies of the kernel for each control point. The next thing to do is we scale each of our copies, and we scale it by the corresponding measurement. Remember that the height of the original kernel at the middle was a value of 1. So if we just multiply each of our shifted copies of the kernel by the corresponding measurement value y, so y1 here, y2 here, y3 and y4, then our kernels will scale up so that their heights correspond to the measurement values at each of the knot point locations. And then finally, the interpolation function that we seek, the one that we're looking for, is basically the sum of these 4 scaled functions. And it can only really be evaluated where we have all the kernels present in each interval. So here is the dashed line that represents the sum of the 4 kernels after they've been shifted and scaled, and the sum is evaluated in the range of the original data. We don't evaluate it outside, beyond x4 or before x1, because in this region here there's only 1 kernel present. And so this is just the notation to represent the sum of the 4 shifted and scaled kernels. Shifted and scaled, all added together. So in general though, we don't have necessarily 4 points. We might have n points, we might take n measurements, So in that case, our interpolation function is going to be equal to each corresponding measurement value multiplied by a shifted kernel function so that it's centered on the corresponding knot point. So y2 multiplied by a shifted kernel that's centered on x2 all the way up to yn multiplied by the correspondingly shifted kernel. And all of this we can write much more compactly as a summation where k ranges from k equals 1 up to k equals n of the corresponding measurement times the correspondingly shifted kernel function. And this formula is very general for interpolation, and we can use it for any different scheme that we have. All we need to do is to make sure that we replace our h function with the appropriate kernel for our interpolation scheme. So here's an example then. If we wanted to do nearest neighbor interpolation, we could use this as our kernel function instead of the previous one. If you recall, the linear one went up at an angle and came down at an angle like that, whereas this one, this is the nearest neighbor kernel, is just a flat line centered at 0 with height 1, and when it reaches plus a half or minus a half, it drops down to 0, and that's the end of it. So in a similar way, we can look at approximation also as a convolution process. It differs very little from viewing interpolation as a convolution. Again, we can use a kernel, but this time it will have to be a different kernel. One example is shown here. This kernel is called a Gaussian kernel. It uses the standard Gaussian function, which is e to the minus x squared over 2 sigma squared. This Gaussian kernel is centered at x equals 0. It's like the distribution for a normal distribution for data that has a mean of 0. And this is a normalization constant here. So if we just write subscript g here to represent our Gaussian kernel, then convolution still works in the same way. We still do this summation, and the summation ranges over all of our observations from k equals 1 up to n, and each time we take yk and we use it to scale the Gaussian function after it has been shifted onto our corresponding knot point. So it's exactly the same as it was before, but we just use a different kernel function this time. So here's an illustration of the process. So we can have some measurement data here ranging along quite a few x values and the y values representing our measurements. And here is one copy of our Gaussian kernel. And as we did before, we shift multiple copies of our Gaussian kernel and scale them by our y values and use that to find a new function, a new continuous function that we can evaluate at all locations along the x-axis that is in the range of our data. And we get this smooth curve here to represent our data. So this now represents our approximation function for original data. So as we noted before, this time we don't actually have to interpolate our data. We don't actually have to go through our data points. We only need to approximate them. Now, because we have this Gaussian kernel, if we just skip back one slide, note that there was a parameter here, sigma, and that is a parameter that can control the width of our kernel. In this example, I've used a value of sigma equal to 1, so that corresponds to a standard deviation of 1. But we can change that parameter sigma, and every time we change that parameter sigma, it will control the width of our kernel. A large value of sigma will correspond to a wide, flat kernel, and a small value of sigma will correspond to a narrow and peaked kernel. And we can use these different choices for sigma so that we can get either a narrow peaked kernel or a medium kernel or a wide flat kernel. So correspondingly with sigma equals a half here, sigma equals 1, and sigma equals 2. And we can use each of these differently shaped kernels. They all have the same functional form, but they have different shapes. And they if we use them to approximate our data with the convolution function, then we can get different curves to represent our approximation of our data. And the wider the kernel that we use, the smoother the overall shape of the approximation function would be. A narrow kernel will give us a more jagged approximation function that will actually try and almost interpolate our data, whereas a wide kernel will just generally follow the overall shape of the data without necessarily approximating it very closely. Now we'll turn to looking at interpolation again, but this time looking at interpolating data that is obtained in a space that has more than one dimension. And for this first part, we're going to look at regular data, and then towards the end of the lecture, we'll look at irregularly spaced data. So sticking to regular data, we can imagine that we might have a two-dimensional function, in this case shown visualized as the image on the left, whereby the value of the function is represented by the brightness of the region. So at any individual point, we can have a high value corresponding to a white intensity, or a low value corresponding to dark or black. And we can imagine that we can take measurements of this 2D function that are sampled on a regular grid, as shown on the right here. So we only get an opportunity to measure this function at a regular grid. In this case, our grid is a 2D grid, a two-dimensional grid. So this two-dimensional grid is sometimes also known as a two-dimensional lattice, and it basically is represented by a discrete set of points with gaps in between them. And these gaps can be in the x direction, and they're shown here by delta x, or they can be in the y direction, as shown by delta y here. Often our sensors, our measuring devices, or whatever grid that we have, will have a spacing that's the same in both dimensions, which makes things a little bit easier. But of course, this is not guaranteed. And our coordinates, any single individual point will have obviously 2 points that we need to specify for it to determine its location. So for example, this point here is determined by x4 and y3. And in general, the coordinates of any point will be given by xi and yj, where I and j can independently range from 1 up to however many elements we have along each dimension. So in this case, we're assuming that I can range from 1 to m, so we're assuming that there are m possible x locations, and j can range from 1 to n, where we're assuming that there are n possible y locations. And in general, if the spacings are uniform, in other words, if we do have a regular grid, which we're assuming that we do, then the location xi is going to be equal to this expression. So if we evaluate this for, say, I equals 1, then we can assume that xi is equal to 0, then x2 would be equal to, substitute 2 in here, would be equal to delta x, and then the next one will be another delta x along, and so forth. So basically we can write out a little function to represent the ith x coordinate and the jth y coordinate in terms of I and j, and in terms of the spacing that there is in between points on our grid. If the data is image data, then the points on our grid are often called pixels. So once we have data defined on a grid, we can start to think about interpolating it. Now, one popular method of interpolating 2D data is called bilinear interpolation. It is just linear interpolation, but because it's been extended to 2 dimensions, we call it bilinear interpolation. So we have x and y are now representing our locations, our knot points, or our grid locations. And so we need a new variable, which we'll call, in this case, z, to represent the measurements that we have at each different location. So each point xi, yj can have a corresponding z value, also indexed by I and j, to represent its value. So here's zij, that's the measurement that we associate with xi, yj here, and this measurement here is zi, comma j plus 1 will correspond to this location here. So we might assume that the different locations all have different values of measurements associated with them, and by looking at the indices of the corresponding x and y locations, we can correspondingly write down a z value for them. And obviously what the interpolation function seeks to do is to find us a function that we can evaluate anywhere in the plane, not just at the grid locations. We want a continuous function, and we want it to be based on the data that is at the grid locations.